7 miles beneath the Antarctic ice, a creature drifts through absolute blackness with eyes the size of soccer balls, glowing, watching, waiting. Its arms align with spinning hooks, sharp enough to shred steel wool. It weighs more than a grand piano, and somehow, after 100 years of searching, we only just filmed it alive for the first time. We are going to dive past crushing pressure and freezing temperatures to meet the Colossal Squid. If you enjoy the journey, drop a like and subscribe. Take a breath. We are going down. Imagine an eye staring back at you from the darkness. An eye nearly 12 inches across, wider than a dinner plate, larger than any eye that has ever existed on any animal in the history of life on Earth. That eye belongs to the Colossal Squid. And everything about this creature seems designed by something that never visited our planet. Scientists have confirmed this. The Colossal Squid holds the record for the largest eyes ever documented in the animal kingdom. We are talking about an organ the size of a soccer ball, filled with a lens as big as an orange, attached to optical lobes in the brain that are larger than the entire visual processing center inside your own skull. This is not guesswork. Researchers measured these eyes directly when they examined specimens brought up from the deep. The results left them stunned. But here is where the story gets stranger. Those massive eyes are not even the most alien feature on this animal. Running down the length of its 2 long tentacles are rows of hooks, not suckers like you see on an octopus. Hooks, sharp, curved, and some of them can rotate 360 degrees. Picture a claw on a swivel, spinning freely to grab whatever it touches and refusing to release. No other squid in its entire family has this adaptation. The Colossal Squid stands alone. Scientists believe these rotating hooks evolved for one purpose: holding onto struggling prey in complete darkness, where a single mistake means losing your meal forever. When you live in a world without light, you cannot chase down something that escapes your grip. You get one chance. These hooks make sure that chance counts. Now consider the scale of this animal. The largest confirmed specimen weighed nearly 1,100 pounds. That is heavier than a polar bear. Heavier than a concert grand piano. The mantle alone, the main body section, stretched over 8 feet long. And the tentacles added even more length, bringing the total size to somewhere around 14 feet. But here is what makes researchers nervous. That specimen was a female, and she was not fully grown. Beak analysis tells us something unsettling. When scientists examine the stomachs of sperm whales, they find squid beaks that the whales cannot digest. These beaks accumulate over time, providing a record of what the whales have eaten. Some of those beaks are significantly larger than the beak of the largest colossal squid ever captured. The math suggests that somewhere in the deep, there are colossal squid weighing 1,300 pounds or more, possibly 1,500. We have never seen them, but the evidence says they exist. What kind of environment produces something like this? The answer is the Southern Ocean surrounding Antarctica. Water temperatures hover just above freezing. Pressure at the depths where adults live would crush a human body instantly. Sunlight disappears entirely below 1,000 feet. And yet this is exactly where the colossal squid thrives. It is not merely surviving in one of the most hostile environments on the planet. It is dominating. The colossal squid sits at the top of the food chain in its ecosystem. Isotopic analysis of its tissues confirms this. It feeds on large fish, including the Patagonian toothfish, which can grow over 6 feet long. It likely eats other squid, and there is evidence it eats members of its own species. We will get to that later. For now, understand this. You are about to learn the secrets of an animal that science has chased for a century. An animal so elusive that only a handful of complete specimens have ever been recovered. An animal that left scars on the bodies of the largest hunters in the ocean. The colossal squid is real. It is out there right now, drifting through the blackness with those enormous glowing eyes. And what those eyes are watching for is something even more terrifying than itself. The year was 1925. A whaling ship operating in the frigid waters near Antarctica had just killed a sperm whale. As the crew processed the massive body, they cut open its stomach expecting to find the usual contents: fish, smaller squid, the half-digested remains of deep-sea creatures. What they found instead was something no scientist had ever documented. 2 severed arm crowns, the muscular base where a squid's arms connect to its body. But these were unlike anything from known species. The arms were thick, powerful, and covered in a combination of suckers and sharp hooks. A naturalist named E. Hamilton preserved the specimens and sent them to the British Museum. There, a researcher named Guy Coburn Robson examined them closely. He realized he was looking at an entirely new species. He named it Mesonicoteuthis hamiltoni. The colossal squid had officially entered the scientific record. But here's the problem. For the next 56 years, that was essentially all we had. 2 arm crowns pulled from a dead whale, no complete body, no living specimen, no photographs. Just the haunting knowledge that somewhere beneath the Antarctic ice, a squid existed that was larger and more heavily armed than anything previously known. The breakthrough came in 1981. A Soviet-Russian trawler operating in the Ross Sea accidentally caught something enormous in its nets. When the crew hauled up their catch, they found a squid measuring over 13 feet long. It was dead. It was female, and it was immature, meaning it had not yet reached full adult size. Scientists identified it as the same species Robson had named decades earlier. Finally, the world had a complete colossal squid to study. But complete specimens remained painfully rare. By 2003, researchers had collected only a second whole individual. This one was a subadult female found floating near the water's edge, likely dying or already dead when discovered. It measured nearly 20 feet, including tentacles. The scientific community celebrated. 2 specimens in over 70 years felt like a treasure. Then came 2007. A New Zealand fishing vessel working in the Ross Sea hooked something while targeting toothfish. The crew realized their catch was not a fish. It was a colossal squid, still alive but badly injured from the capture process. They carefully brought it aboard and froze the entire animal to preserve it for research. When scientists later thawed and examined the specimen, they recorded its weight at nearly 1,100 pounds. Its mantle measured over 8 feet. Its eyes, though partially collapsed from death and freezing, were estimated to have been 12 to 16 inches in diameter when alive. This specimen now sits on display at the Museum of New Zealand. It remains the largest colossal squid ever examined by scientists. But the beaks found in whale stomachs tell us bigger individuals are out there. We just have not caught them. Why is this animal so hard to find? The answer lies in its environment. The southern ocean covers roughly 8 million square miles. The colossal squid lives at depths ranging from 1,000 to over 7,000 feet. It actively avoids light and noise, meaning research equipment often scares it away before cameras can record anything. And unlike fish that school together in predictable locations, this squid appears to live a solitary existence, drifting alone through the vast emptiness of the deep. As of 2015, only 12 complete colossal squid had ever been documented. Half of those were juveniles or subadults. The other half included only a few true adults. 55 beaks have been recovered from whale stomachs and other sources. But a beak without a body tells you little about how the animal actually lived. For a full century, the colossal squid remained more legend than science. Researchers knew it existed. They had the pieces to prove it, but no one had ever seen one alive in its natural home. That changed in 2025, and what the EU cameras revealed was nothing like the monster everyone expected. Let that number settle in your mind. 1,100 pounds, possibly 1,500 for the largest individuals. The colossal squid is the heaviest invertebrate currently alive on Earth. Not the longest. That title belongs to its cousin, the giant squid, which can stretch over 40 feet thanks to its extremely long and slender tentacles. But in terms of raw mass, the colossal squid dominates. It is built like a wrestler, where the giant squid is built like a swimmer. To understand what this means, you need to compare it to other squid. A typical squid you might see at a fish market has a mantle about 12 inches long and weighs maybe half a pound. The colossal squid's mantle alone can exceed 8 feet. Its body is wide, dense, packed with muscle. Scientists describe the difference like comparing a snake to a bulldog. Both are predators, but one is built for constriction and the other is built for power. This size did not happen by accident. The colossal squid exhibits something called polar gigantism. Animals living near the poles often grow significantly larger than their relatives in warmer waters. The exact reasons are still debated, but researchers believe it relates to oxygen availability. Cold water holds more dissolved oxygen than warm water. More oxygen means cells can grow larger, and metabolisms can support bigger bodies. The Antarctic provides perfect conditions for producing giants. But size creates problems. A body weighing half a ton requires enormous amounts of energy to move quickly. Chasing prey through the water would burn calories the squid might not be able to replace in an environment where food is scarce. So how does the colossal squid solve this problem? It cheats. Its body contains high concentrations of ammonium chloride. Ammonia is lighter than seawater. By saturating its tissues with this chemical, the squid achieves something close to neutral buoyancy. It can hover in the water column with almost no effort. No constant swimming required. No wasted energy. This adaptation has a side effect that matters to anyone who might consider eating one. Ammonia tastes terrible. The flesh of a colossal squid reportedly has an unpleasant flavor and odor that makes it essentially inedible for humans. Sperm whales apparently do not mind, but we certainly would. Now picture this animal in its environment. The Southern Ocean is not a single, uniform habitat. It has layers. The top few hundred feet receive sunlight and support most of the food chain. Below that lies the mesopelagic zone, stretching from around 650 feet to over 3,000 feet. This is the twilight zone, where light fades to almost nothing. Deeper still is the bathypelagic zone, starting around 3,000 feet and extending past 10,000. Here there is no light at all. Temperatures hover near freezing. Pressure would crush an unprotected human instantly. Adult colossal squid spend most of their lives in the mesopelagic and bathypelagic zones. Juveniles stay higher in the water column where food is more abundant. As they grow, they descend. Scientists believe this vertical migration reduces predation pressure. Staying deep means fewer predators can reach you. It also means living in a world of permanent night, where your survival depends entirely on senses that humans can barely comprehend. Consider what it takes to exist here. You cannot see your prey until it is within striking distance. You cannot hear the approach of predators the way surface animals can. You must conserve every calorie because your next meal might be days or weeks away. And yet you must remain alert because somewhere in that darkness, something is always hunting. The colossal squid has adapted to all of this. Its body is a masterpiece of deep-sea engineering. But its most remarkable features are not its size or its hooks. They are its eyes. And what those eyes evolve to detect will change how you think about survival. March 9th, 2025. A research vessel named Falkor floated in the frigid waters near the South Sandwich Islands. Below deck, scientists monitored screens showing live footage from a remotely operated vehicle called Seibel. The submersible had descended nearly 2,000 feet into the South Atlantic. And then, drifting through the frame, came something that made researchers gasp. A colossal squid. Alive. Swimming freely in its natural habitat. For the first time in the 100 years since the species was identified, humans were watching this animal exist in the deep sea as nature intended. The squid in the footage was small, about 12 inches long, a juvenile, probably what scientists would describe as a teenager in human terms. Its body was almost completely transparent, giving it the appearance of a delicate glass sculpture floating through the darkness. You could see its internal organs through its skin. Its eyes, proportionally enormous even at this young age, reflected light from the submersible's cameras. Why did it take so long to achieve this moment? The answer involves everything working against researchers trying to study this animal. First, consider the search area. The colossal squid lives throughout the circumantarctic Southern Ocean. That is an area roughly the size of North America. Within that vast region, the squid occupies depths that require specialized equipment to reach. You cannot simply dive down and look around. You need submersibles capable of withstanding crushing pressure, and those machines are expensive, rare, and difficult to deploy. Second, the colossal squid has evolved to avoid exactly the kind of detection that research equipment provides. Its enormous eyes are among the most sensitive light detection organs ever developed by any animal. Scientists believe these eyes can spot the faint glow of bioluminescent creatures disturbed by approaching predators from over 400 feet away. Research submersibles, by comparison, are bright and loud. They light up the darkness and produce noise that travels far through water. The squid almost certainly detects this equipment long before cameras can record anything useful. Most of the time, it simply swims away. Third, the colossal squid appears to respond to threats by freezing in place. If it cannot escape quickly, it may stop moving entirely, hoping to avoid notice. This behavior makes sense when your predator uses echolocation and movement detection, but it creates problems for researchers using visual observation. A motionless squid in a vast dark ocean is nearly impossible to find. Finally, there is the matter of specimen collection. Nearly everything we knew about colossal squid before this footage came from dead or dying animals. Specimens hauled up by fishing vessels. Remains extracted from whale stomachs. The occasional individual found floating near the waterline in the final stages of life. Living colossal squid in good health exist only in the deep, and the deep does not give up its secrets easily. The 2025 sighting happened partly by luck. The research team was not specifically hunting for colossal squid. They were conducting a broader survey of marine life around the South Sandwich Islands. A viewer watching the live stream of the dive spotted the animal and alerted experts, who quickly confirmed its identity based on the distinctive hooks visible on its arms. Even then, the footage lasted only minutes before the squid drifted away. But those minutes revealed something unexpected. The colossal squid in the video did not look like a monster. It looked fragile, beautiful, almost delicate. Its fins were so thin they were barely visible. Its movements were slow and graceful. One researcher described it as resembling a glass sculpture. This single observation challenged decades of assumptions about what the colossal squid actually is. Perhaps the creature lurking in Antarctic darkness is not the aggressive hunter popular culture imagined. Perhaps it is something stranger, something quieter, something waiting. Stare into the eye of a colossal squid, and you will notice something unusual. Beside the lens, positioned at the front of each eyeball, sits a rectangular structure that produces light. These are photophores, biological light organs. The colossal squid has built-in headlights mounted directly on its eyes. This feature is confirmed. Scientists examining preserved specimens documented these structures in detail. Each photophore contains symbiotic bacteria that produce light through a chemical reaction called bioluminescence. The light stays on constantly. The squid cannot turn it off the way you might flip a switch, but it can control how much light escapes by adjusting tissues around the organ. Why would any animal want glowing eyes? In absolute darkness, this seems like a terrible idea. You would be announcing your location to every predator in the area. But the colossal squid is not using these lights carelessly. It is using them as precision hunting tools. Here is how scientists believe it works. The colossal squid's eyes face forward, giving it binocular vision. This means both eyes can focus on the same point simultaneously, allowing the squid to judge distance with remarkable accuracy. When the squid spots potential prey, it aims its eyes directly at the target. The photophores illuminate the area immediately in front of its face, revealing exactly where its arms and tentacles need to strike. Think of it like a flashlight mounted on a rifle. The light shows you precisely where your weapon is pointing. In the eternal night of the deep sea, this tiny advantage could mean the difference between eating and starving. But there is another theory that makes the photophores even more interesting. Some researchers believe the colossal squid uses its eye lights for a form of camouflage called counter-illumination. When predators look up from below, they see the faint glow of sunlight filtering down from far above. Any object between them and that light creates a dark silhouette. The colossal squid's photophores might produce just enough glow to match the ambient light, erasing its shadow and making it invisible to threats approaching from beneath. This strategy is common among deep-sea animals. Many species have photophores on their undersides, specifically for this purpose. The colossal squid takes the concept further by integrating the lights directly into its visual system. Consider what this tells us about evolution in the deep ocean. Light is so important down here that animals have developed organs specifically to produce it. They have bacteria living inside their bodies whose only job is generating photons. They have structures that focus, filter, and direct that light with precision that rivals human engineering. And they have been doing this for millions of years, long before humans invented the flashlight. The colossal squid's photophores also raise questions we cannot yet answer. Do they serve additional functions we have not discovered? Can the squid modulate the color or intensity of the light to communicate with others of its kind? Does the glow attract certain prey species, the way anglerfish lure victims with their bioluminescent lures? We do not know. The handful of specimens examined were dead and preserved. Their photophores were no longer functioning. The brief footage from 2025 showed a juvenile whose photophores may not have been fully developed. Until researchers observe an adult colossal squid using its eye lights in real time, these questions remain open. What we know for certain is this: the colossal squid sees in ways we are only beginning to understand. Its eyes are marvels of biological engineering, equipped with features that seem almost technological. But those eyes evolved to detect something specific, something massive, something hunting through the darkness with senses the squid cannot perceive. Every squid has 8 arms and 2 longer tentacles. This basic body plan has existed for hundreds of millions of years, but the colossal squid modified the design in ways that set it apart from every other member of its family. Running down the middle portion of each tentacle are rows of hooks. Not suckers, hooks. Sharp, curved structures made of chitin, the same material found in insect exoskeletons. There are 22 to 25 of these hooks, arranged in 2 parallel rows on the club-shaped end of each tentacle. Each hook sits in a small depression connected to a short stalk. And here is what makes them extraordinary. They can rotate. Scientists at the Museum of New Zealand examined these hooks in detail during dissections. They documented that each tentacular hook can swivel 360 degrees. Some can even spin a full 720 degrees before the tissue limits further movement. This means the hooks are not fixed in one position. They can pivot freely to maintain grip on whatever they contact. Imagine grabbing a fish in total darkness. You cannot see what you are holding. You cannot adjust your grip visually. The fish is struggling, twisting, doing everything possible to escape. If your hooks were rigid, the prey might simply rotate out of your grasp. But if your hooks can spin to match the movement, they dig in deeper with every twist. Escape becomes nearly impossible. Researchers are still uncertain whether the squid actively controls each hook, or whether the hooks swivel passively in response to prey movement. Both scenarios work effectively. Active control would allow precision targeting. Passive swiveling would require less neural investment while still preventing escape. Either way, the result is a gripping system unlike anything else in the squid family. The tentacles are used for initial prey capture. The squid likely drifts in darkness until something edible comes within range. Then the tentacles shoot forward, snagging the target with those rotating hooks. Once the prey is secured, the tentacles pull it toward the arms. The arms have hooks too, but these are different. They are larger, sturdier, fixed in position. Most have 3 points instead of 1, creating a structure that grips from multiple angles simultaneously. These arm hooks are embedded deeply in muscular sheaths, making them extremely difficult to dislodge. Their job is not to catch prey, their job is to hold prey still while the squid kills it. Between the hooks on the arms are rings of suckers. These are not the soft, flexible suckers of an octopus. Colossal squid suckers have sharp serrated edges made of chitin. They can cut into flesh as they grip. Toothfish hauled up by fishing vessels sometimes bear circular scars that match these suckers exactly. The fish survived an attack. Many others did not. Put all of this together and you have an animal equipped with weapons at multiple scales. Long-range rotating hooks on the tentacles for initial capture. Medium-range 3-pointed hooks on the arms for immobilization. Close-range serrated suckers for additional grip and cutting. And at the center of it all, a beak. The colossal squid has the largest beak of any known squid species. Made of the same chitin as the hooks, it operates like a parrot's beak, slicing through flesh with scissor-like efficiency. Once prey is pulled to the mouth, the beak tears it into pieces small enough to swallow. No other squid in the Cranchidae family has hooks. The colossal squid is the only hooked member of a group containing about 20 species. This makes it an evolutionary outlier. Something in its environment drove the development of these weapons when its closest relatives never needed them. What prey requires this level of armament? What struggles hard enough to justify rotating hooks and 3-pointed blades? The answer involves fish that grow over 6 feet long, and sometimes other colossal squid. The arm hooks deserve special attention because they reveal something important about how this animal feeds. Unlike the tentacle hooks, which swivel freely, the arm hooks are anchored solidly in place. They are surrounded by thick muscular tissue that holds them rigid. Each hook has a complex base structure buried deep in the flesh, making it nearly impossible to pull out. Most arm hooks have 3 points. One large main claw curves outward like a talon. 2 smaller secondary cusps sit near the base, angled to catch anything that slips past the primary point. This design maximizes holding power. Prey cannot simply slide off. The 3 points work together to lock tissue in place. Scientists describe this as a ratchet system. Once something is hooked, pulling away only drives the points deeper. The geometry works against escape. Every struggle makes the grip tighter. Now consider the scale. A full-grown, colossal squid has 8 arms, each bearing multiple rows of these 3-pointed hooks interspersed with serrated suckers. When the squid wraps its arms around prey, dozens of these weapons engage simultaneously. The prey is not merely held, it is locked in a cage of blades. Evidence of these hooks appears on animals that survived attacks. Antarctic toothfish brought up by commercial fishing operations sometimes display distinctive wounds, circular sucker marks, parallel scratches matching hook placement. Between 2011 and 2014, researchers documented 71 toothfish out of 8,000 examined showing clear signs of colossal squid attack. That means roughly 1% of toothfish caught in that region had encountered a colossal squid and lived to bear the scars. The toothfish itself is not small. Adults commonly reach 6 feet in length and can weigh over 200 pounds. This is a substantial fish, muscular and powerful, yet the colossal squid attacks them successfully. The hooks make this possible. Without a gripping system this effective, tackling such large prey would be impractical. But here is where the story takes a darker turn. Scientists examining the stomach contents of a female colossal squid found something unexpected. Squid remains, pieces of another colossal squid. The species is likely cannibalistic. This discovery came from a specimen caught in the Preeds Bay region of Antarctica. When researchers analysed what the animal had eaten, they identified tissue that matched its own species. Cannibalism is not unusual among squid. Many species eat their own kind when other food is scarce. But for an animal as rare and difficult to study as the colossal squid, this finding raised immediate questions. Does cannibalism occur regularly, or only under extreme circumstances? Do adults prey on juveniles, or do similar-sized individuals fight each other? Are the hooks and suckers designed partly to combat others of the same species? We cannot answer these questions yet. The sample size is too small, but the implications matter. If colossal squid routinely prey on each other, it affects population estimates and food web models. An animal that eats its own kind has different ecological dynamics than one that relies solely on other species. The three-pointed hooks may serve dual purposes: catching fish, defeating rivals. In an environment where meals are rare and competition is fierce, weapons that work against both food and competitors would provide significant advantages. Sperm whales frequently show scars believed to come from colossal squid hooks. Circular marks and parallel scratches appear on their skin, evidence of violent encounters in the deep. The whales nearly always win these battles, but the squid does not go quietly. Those hooks dig in. They hold. They leave marks that last a lifetime on the largest predators in the ocean. And that is exactly what they evolved to do. A half-ton animal drifting motionless in the water column presents an engineering problem. Gravity wants to pull it down. Swimming constantly to stay in place would burn precious energy. The colossal squid solved this problem chemically. Its tissues are saturated with ammonium chloride. This compound is lighter than seawater. By maintaining high concentrations throughout its body, the squid achieves something close to neutral buoyancy. It can hover in place with almost no effort. No constant fin movement, no jet propulsion, just floating. This adaptation appears throughout the deep-sea squid world, but the colossal squid takes it to an extreme. The ammonia concentration in its tissues is exceptionally high. Researchers handling specimens describe the flesh as having a strong chemical odor. When touched, it feels soft and somewhat gelatinous, despite the animal's size. The benefits are clear. Energy conservation becomes possible at scales that would otherwise be unmanageable. An 1,100-pound squid that needed to swim constantly would require enormous amounts of food just to maintain position. In the deep Antarctic, where prey is scattered and encounters are unpredictable, such energy demands could be fatal. The ammonia buoyancy system allows the squid to wait, to drift, to conserve calories for the moments when they truly matter. But nothing in biology comes free. The ammonia solution creates trade-offs that shape the squid's entire lifestyle. First, ammonia tastes bad. Really bad. The flesh of colossal squid is reportedly unpalatable to humans because the chemical gives it an unpleasant flavor and smell. This probably does not bother sperm whales, which gulp their prey whole without chewing, but it may deter some smaller predators that would otherwise consider juvenile colossal squid a worthwhile meal. Second, ammonia affects tissue density in ways that limit muscle performance. Researchers note that ammonia-rich squid often have softer, less powerful muscles than their ammonia-free relatives. The colossal squid's flesh has been described as flabby to the touch. This suggests it may not be capable of the explosive bursts of speed that other squid species use for hunting and escape. For years, this observation fueled speculation about the colossal squid's hunting behavior. Early assumptions pictured it as an aggressive pursuit predator, actively chasing down prey like a torpedo with tentacles. The ammonia evidence contradicted this image. An animal with soft, buoyant tissues probably cannot sustain high-speed chases. Something else must be happening. Scientists now believe the colossal squid is an ambush predator. It drifts in darkness, conserving energy, waiting for prey to come close enough to strike. When the moment arrives, it uses a quick burst of tentacle extension rather than a prolonged chase. The rotating hooks do the work of holding prey that the squid's muscles might not be strong enough to restrain otherwise. This hunting strategy makes sense for the deep Antarctic environment. Cold water slows metabolisms. Scattered prey makes active hunting inefficient. The ammonia buoyancy system and ambush behavior fit together as complementary adaptations to the same harsh conditions. There is one more implication worth considering. If the colossal squid cannot swim fast, it probably cannot flee effectively either. When predators approach, it has limited options: freeze and hope to go unnoticed, deploy ink to obscure its location, or stand and fight with those fearsome hooks. Against most threats, these defenses probably work. But against the one predator that specializes in hunting deep-sea squid, the colossal squid faces a problem that no amount of ammonia can solve. That predator dives over 7,000 feet. It can hold its breath for 90 minutes. And it uses biological sonar to find prey in complete darkness. Numbers tell a story here that words alone cannot capture. A 500-kilogram colossal squid needs approximately 30 grams of food per day. That is roughly 1 ounce. For an animal weighing over 1,100 pounds, the daily food requirement is about the same weight as a small handful of coins. Scientists reached this conclusion by calculating the squid's metabolic rate based on water temperature and body mass. In the near-freezing waters of the Antarctic, metabolisms run slowly. Cold-blooded animals living in cold environments burn fewer calories than their warm water counterparts. The colossal squid exists at the extreme end of this spectrum. For comparison, consider a similarly sized warm-blooded predator. A large shark of the same mass would need to eat several pounds of food daily to maintain body functions. A marine mammal would require even more. The colossal squid's requirements are a tiny fraction of these amounts. This slow metabolism explains many otherwise puzzling observations. It explains why the squid can afford to drift rather than hunt actively. It explains why specimens often appear sluggish or lethargic when encountered. It explains why the ammonia buoyancy system makes evolutionary sense. When you need only an ounce of food per day, conserving energy becomes more important than moving quickly. But metabolic rate also affects growth and lifespan in ways researchers are still investigating. Squid in general live fast and die young compared to other marine animals. Most species complete their entire life cycle in 1 to 2 years, growing rapidly, reproducing once, and then dying. The colossal squid may follow a similar pattern, but its slow metabolism could stretch this timeline considerably. Unfortunately, no one has observed a colossal squid long enough to determine its actual lifespan. The specimens we have are snapshots frozen in time. They tell us what the animal looked like at the moment of death, but nothing about how long it took to reach that size or how much longer it might have lived. Scientists use beak size and growth rings to estimate age in other squid species. Similar analysis on colossal squid beaks suggests they may live longer than typical squid, possibly several years. But this remains theoretical. The sample size is too small for the confident conclusions. The slow metabolism also affects how scientists model the squid's role in the Antarctic food web. If colossal squid need little food individually, their impact as predators is smaller than their body size might suggest. They are not removing large quantities of fish from the ecosystem. They are selective, occasional feeders taking what they need, and no more. At the same time, their role as prey becomes more interesting. Sperm whales consume enormous quantities of squid. Estimates suggest that colossal squid may make up 77% of the biomass these whales eat in Antarctic waters. That means the whales are getting most of their energy from an animal that itself requires almost no energy to maintain. This creates an unusual dynamic. The colossal squid acts as a kind of energy battery, slowly accumulating resources over time and then transferring them to whale populations in sudden, violent encounters. The squid's patience becomes the whale's gain. But here is what keeps researchers guessing. If the colossal squid truly eats so little, how does it grow so large? Where does the mass come from? Growth requires material, and material comes from food. An animal eating 1 ounce per day should not be able to build a body weighing half a ton. The answer may involve extremely efficient conversion of food to tissue, or it may involve feeding patterns that vary more than current models suggest. Perhaps young squid eat more aggressively before their metabolisms slow with maturity. Perhaps adults occasionally gorge when prey is abundant. The truth is, we do not know. The deep keeps its secrets well. 30 grams. Picture a small egg. That is approximately how much food a full-grown colossal squid requires in a 24-hour period. This number sounds impossible until you understand the environment that shaped it. The deep Antarctic Ocean is not rich with food. Unlike coastal waters where nutrients cycle rapidly and support dense populations of fish, the bathypelagic zone is sparse. Prey is scattered. Encounters are unpredictable. An animal that evolved to require large meals regularly would face frequent starvation. The colossal squid evolved the opposite approach. It needs almost nothing. This frugality is built into every aspect of its biology. The ammonia buoyancy system eliminates the caloric cost of staying afloat. The slow metabolism reduces baseline energy requirements to minimal levels. The ambush hunting strategy avoids the expense of active pursuit. Everything about this animal is designed to minimize energy expenditure. Think of it as biological efficiency taken to an extreme. Where other predators burn fuel constantly, the colossal squid runs on idle. It can afford to wait days or weeks between meals because its body simply does not demand more. But this efficiency creates constraints that shape behavior in profound ways. An animal with almost no caloric reserves cannot afford expensive activities. Fast swimming, extended chases, frequent mating displays, territorial battles, all of these behaviors cost energy that the colossal squid may not have available. Instead, it conserves. It drifts. It watches with those enormous eyes. When opportunity presents itself, the squid acts decisively. One quick strike, one burst of tentacle extension. If the attempt fails, the squid returns to waiting mode rather than pursuing. The energy math makes extended effort impractical. This lifestyle seems almost meditative by predator standards. No frantic hunting, no constant motion, just presence, awareness, and occasional, precise violence. Some researchers have suggested the colossal squid might be more scavenger than hunter, consuming dead or dying animals that sink from above rather than actively killing prey. The evidence currently does not support this. Toothfish bearing attack scars prove that living prey is taken. The hooks and beak are clearly predatory adaptations. But scavenging may supplement the diet when opportunities arise. In an environment where calories are precious, refusing easy meals would be counterproductive. The 30-gram daily requirement also explains something about the squid's population dynamics. An animal that eats so little does not deplete prey populations the way voracious feeders do. Colossal squid can coexist with their prey species without driving them toward extinction. The Antarctic ecosystem can support large squid because each individual makes such modest demands. Contrast this with sperm whales, which consume massive quantities of squid daily. A single whale might eat over a ton of squid in a day. The whale's metabolism runs hot compared to its cold-blooded prey. It needs constant fuel to maintain body temperature in frigid waters. Where the squid sips, the whale gulps. This metabolic mismatch creates the strange relationship between these two species. The colossal squid spends years slowly building body mass on minimal food. The sperm whale consumes that accumulated mass in seconds during a successful hunt. The squid's patience becomes the whale's meal. Evolution shaped both animals perfectly for their roles. The squid to conserve, the whale to consume. Both strategies work. But when they collide in the darkness of the deep, the outcome is rarely in doubt. Forget what you think you know about giant squid attacks from movies and legends. The colossal squid does not chase ships. It does not drag sailors into the deep. It does not engage in high-speed pursuit of anything. The reality is stranger and in some ways more unsettling. This animal waits. Scientists believe the colossal squid is what they call a sit-and-float predator. It drifts in the darkness, nearly motionless, using minimal energy to maintain position. Its enormous eyes scan the blackness for movement. Its arms hang loosely, hooks ready. It could wait hours, days, weeks. Time means little when your metabolism barely ticks. When prey comes close enough, the squid acts with sudden precision. The tentacles shoot forward, hooks engaging on contact. The rotation mechanism locks onto struggling flesh. The arms wrap around, 3 pointed hooks digging in. The beak moves toward the trapped animal. From first contact to first bite might take only seconds, and then the waiting begins again. This hunting strategy makes sense given everything we know about the squid's physiology. Its ammonia-rich tissues are soft. Its muscles are not built for sustained power output. Extended chases would drain energy reserves that take weeks to rebuild. The ambush approach conserves resources while still allowing successful predation. But it also means the colossal squid is essentially passive. It does not control when it eats. It depends on prey wandering into range. If nothing comes close, the squid goes hungry. This vulnerability is balanced by the extremely low caloric requirements. Even rare meals can sustain an animal that needs only an ounce of food per day. The toothfish evidence supports this model. Researchers found that colossal squid attacks on toothfish were relatively uncommon. Out of 8,000 fish examined, only 71 showed attack wounds. This suggests colossal squid do not encounter or attack toothfish frequently. When they do, the attacks often fail. The fish escape bearing scars rather than becoming meals. A highly active pursuit predator would show different numbers. It would encounter more prey. It would have higher success rates. The low attack frequency suggests the squid is not hunting aggressively. It is waiting, striking occasionally, and letting many potential meals pass without engagement. This passivity challenges the monster imagery that has surrounded the colossal squid since its discovery. We imagined a kraken, a terror of the deep actively seeking victims. What we found instead is something closer to a trap. Dangerous when triggered, but otherwise still. There is beauty in this strategy. An animal perfectly adapted to its environment, making no unnecessary movements, demanding almost nothing from the world around it. It exists in equilibrium with the sparse Antarctic ecosystem in ways that aggressive predators cannot match. But do not mistake patience for weakness. When the colossal squid strikes, it strikes with weapons that leave scars on animals many times its size. The 3-pointed hooks, the rotating blades, the serrated suckers. These evolved because prey fights back. Even an ambush predator needs to hold what it catches. And occasionally, the colossal squid encounters something it cannot hold. Something that strikes first. Something that has been hunting colossal squid for millions of years. Here is a fact that changes everything you think you know about the colossal squid's massive eyes. Those 12-inch globes are probably not designed primarily for finding food. They evolved mainly to detect predators. This conclusion comes from research comparing eye size to body size across many species. For an animal of the colossal squid's mass, hunting in typical deep-sea conditions would require eyes about 4 inches in diameter. That would provide sufficient visual acuity to spot prey at distances relevant to ambush predation. But the colossal squid has eyes nearly 3 times that size. Why the excess? The answer involves sperm whales. These massive predators dive thousands of feet into the darkness specifically to hunt squid. They use echolocation to find prey, producing clicking sounds and listening for echoes. This sonar works extremely well. Sperm whales can detect squid from significant distances using sound alone. But here is the critical detail. In the final moments before an attack, sperm whales switch from sonar to vision. They close the distance using their eyes rather than their ears. This transition happens within roughly 400 feet of the prey. And 400 feet is exactly where the colossal squid's oversized eyes provide an advantage. As a sperm whale descends through the water column, it disturbs bioluminescent organisms. These tiny creatures flash when touched, creating a faint glow around the whale's body. In the absolute darkness of the deep, this glow is visible. The colossal squid's enormous eyes can detect this disturbance from beyond 400 feet, well outside the range where the whale's visual hunting becomes effective. In other words, the squid can see the whale coming before the whale can see the squid. This early warning system provides precious seconds. The squid can begin evasive action while the whale is still using sonar. It can flee before the final visual approach begins. Those massive eyes are not searchlights for hunting. They are alarm systems for survival. The photophores mounted on the eyes serve a related function. By producing a faint glow that matches ambient bioluminescence, the squid can mask its silhouette from predators looking upward. The light organs and the oversized eyes work together as a defensive system rather than an offensive one. This realization shifts our understanding of the colossal squid completely. We assumed those eyes meant aggressive hunting, visual dominance, a predator that sees everything. Instead, they mean fear, vigilance, an animal that evolved primarily to escape something bigger than itself. The irony is profound. The largest invertebrate on Earth, armed with hooks and blades and the most massive eyes in animal history, is fundamentally a prey species. It hunts, yes. It kills, certainly. But its most impressive adaptations exist not to capture food, but to avoid becoming food. And those adaptations are not always successful. Sperm whales remain the colossal squid's primary predator. Their stomachs contain more colossal squid beaks than any other evidence suggests these animals are hunted extensively. The giant eyes help. They provide warning. But they cannot guarantee survival. When the whale gets close enough, the squid's options narrow. Fight back with hooks that leave scars but rarely stop the attack. Release ink that briefly obscures vision. Or simply die in the jaws of the largest predator these depths have ever known. Let that distance settle into your mind. 400 feet. That is the estimated range at which a colossal squid can detect an approaching sperm whale based on the bioluminescent disturbance the whale creates. Beyond that range, the squid is essentially blind to the threat. Within that range, escape becomes a race against something faster. Scientists reach this estimate through careful analysis of eye structure and light detection capabilities. The colossal squid's eyes contain millions of photoreceptors concentrated in arrangements that maximize sensitivity to faint light. The lens focuses images with precision comparable to camera optics. The optical lobes in the brain that process visual information are enormous, larger than a human's entire visual cortex. All of this biological machinery exists for one primary purpose: seeing things that produce almost no light in an environment where almost no light exists. Bioluminescence is the key. The deep ocean is not entirely dark. Organisms throughout the water column produce their own light through chemical reactions. Some use this light to attract prey, others use it for communication. Many produce light involuntarily when disturbed. Touch a certain jellyfish, and it flashes. brush past certain plankton and they glow. A sperm whale descending through this environment creates a cascade of tiny flashes. Each contact with a bioluminescent organism produces a brief spark. Hundreds of these sparks per second trace the whale's outline in light. The effect is subtle, far too faint for human eyes to detect. But the colossal squid did not evolve for human conditions. Those soccer ball-sized eyes gather light with phenomenal efficiency. They can detect gradients of brightness so faint that our instruments struggle to measure them. A glowing disturbance 400 feet away, invisible to nearly everything else in the ocean, registers on the squid's visual system like a warning beacon. 400 feet of advance notice. What can the squid do with that time? The honest answer is probably not enough. Sperm whales swim faster than colossal squid. They are also more maneuverable than their bulk suggests. A squid that tries to flee directly away from an approaching whale is likely to be caught. The whale's sonar continues functioning throughout the chase, providing constant position updates even when visual contact has not yet been established. The squid's best strategy may be deception rather than speed. By freezing in place, it can attempt to avoid triggering the whale's sonar return. Moving objects produce stronger echoes than stationary ones. The squid might also change its body orientation to present a smaller acoustic profile. These tactics work against echolocation in ways that fleeing does not. The ink defense provides another option. Colossal squid can release clouds of dark fluid that obscure vision and may interfere with sonar returns. A well-timed ink deployment might create confusion during the whale's final approach, allowing the squid to slip away in an unexpected direction. But all of these defenses are uncertain. They sometimes work and sometimes fail. The whale has been hunting these squid for millions of years. It knows the defenses. It has countermeasures. The 400-foot detection range is not a guarantee of safety. It is a chance. An opportunity that evolution provided against an opponent that would otherwise kill with no warning at all. Sperm whales produce the loudest sounds in the animal kingdom. Their echolocation clicks can reach 230 decibels. That is equivalent to standing next to a jet engine at full throttle. These clicks are not communication. They are hunting tools. Each click bounces off objects in the water and returns as an echo that tells the whale exactly where prey is located. The colossal squid cannot hear any of it. Squid have organs called statocysts that detect sound vibrations, similar in function to the human inner ear. But these organs respond only to low-frequency sounds below about 500 Hz. Whale sonar operates at much higher frequencies, in ranges that squid statocysts simply cannot detect. The clicks that tell the whale everything about the squid's location are completely silent from the squid's perspective. This deafness is not a design flaw, it is an adaptation to the acoustic environment where squid evolved. Low-frequency sounds travel farther in water and provide information about large-scale movements. High-frequency sounds attenuate quickly and are used mainly by echolocating predators that evolved more recently. Squid never needed to hear high-frequency sounds because for most of their evolutionary history, nothing that hunted them used such sounds. Then, sperm whales appeared. These mammals evolved echolocation systems specifically optimized for finding squid in deep water. They produce high-frequency clicks that provide precise location data for soft-bodied prey. From the whale's perspective, this was an evolutionary breakthrough. From the squid's perspective, it was the arrival of an invisible predator. Consider what this means for the colossal squid. A sperm whale can dive to depths exceeding 7,000 feet. It can remain submerged for 90 minutes or more. Its sonar can detect squid from distances that would take minutes to cross. And the squid has no awareness that any of this is happening until the whale gets close enough to disturb bioluminescent organisms within visual range. The 400-foot detection. Distance sounds impressive until you realize the whale might have been tracking the squid from half a mile away. The squid's first warning comes when the whale is already in final approach, making targeting decisions, preparing to strike. Evolution provided no defense against this acoustic blindness. The statocysts that detect low-frequency sound cannot be modified to hear high frequencies. The fundamental physics of the organ does not permit it. The colossal squid is stuck with the hearing system it inherited from ancestors that never faced echolocating predators. The only answer was visual detection. Those enormous eyes evolved partly because sound was useless against the squid's primary threat. The bioluminescent warning system works. It gives the squid a chance, but it works only at close range, and only when the whale has already committed to attack. This predator-prey dynamic has played out countless times in the darkness of the Southern Ocean. A whale descends, clicking, constantly, building an acoustic map of everything below. A squid drifts, deaf to the approach, relying on eyes that cannot see far enough. The distance closes. The whale gets visual confirmation. The squid finally sees the danger. Sometimes the squid escapes, sometimes it dies. The statistics favor the whale heavily, but occasionally the squid fights back in ways that leave lasting marks. Those battles leave scars that scientists can read like a history written in flesh. The colossal squid's lifestyle changes dramatically as it grows. Juveniles live in fundamentally different conditions than adults. Understanding this transition reveals how the species manages to survive in one of the harshest environments on Earth. Young colossal squid, those with mantles shorter than about 16 inches, occupy the upper layers of the ocean. They have been found at depths ranging from the water's edge down to roughly 3,000 feet. This zone receives at least some sunlight. It supports more abundant prey. It is also more accessible to researchers, which is why most colossal squid specimens ever captured have been juveniles. This shallow water phase makes biological sense. Young animals need to grow rapidly. Growth requires food. The upper ocean layers contain far more potential prey than the sparse bathypelagic depths where adults live. A juvenile colossal squid can find the calories it needs to build body mass before descending into environments where such meals are rare. The 2025 footage captured a juvenile at roughly 600 feet. Scientists described it as having lost some baby features, but not yet reached adult proportions. Its body was almost completely transparent, allowing organs to be seen through the skin. This transparency is common among members of the glass squid family, and likely provides camouflage against predators hunting by sight. As the squid ages and grows, it gradually moves deeper. Adolescents are found between 500 and 2,000 meters. Adults rarely come shallower than that. The descending pattern correlates with increasing body size and decreasing transparency. Larger squid need less protection from size-limited predators. They also benefit from the reduced competition in deep water. Scientists believe this vertical migration serves multiple purposes. First, it separates life stages, reducing cannibalism between adults and juveniles. If adults stayed in shallow water, they would encounter and likely eat young squid. The depth separation keeps generations apart. Second, it provides predator avoidance. Many animals that eat juvenile squid cannot dive to the depths where adults live. By descending as it grows, the colossal squid enters an environment with fewer and fewer things capable of killing it. Only sperm whales, certain deep-diving beaked whales, and large sleeper sharks can reach adult colossal squid in their deep refuges. Third, it may relate to reproduction, although no one has observed colossal squid mating. Deep water likely provides better conditions for encounters between adults. The sparse population density in the bathypelagic zone would make finding mates difficult at shallow depths, where individuals might pass without meeting. Concentration in a narrower depth band increases encounter rates. The transition from transparent juvenile to opaque adult involves significant physiological changes. The body becomes denser. The muscles thicken. The ammonia concentration increases to provide buoyancy at greater pressures. The metabolism slows to match reduced food availability. The animal that emerges from this transformation is fundamentally different from the one that began it. This transformation takes years. Exactly how many years remains unknown. The slow metabolism suggests extended development compared to other squid species. Some researchers estimate colossal squid may live 5 years or more, though this is speculative. During those years, the squid experiences an entire world that adult existence will never include. Sunlight, abundant prey, the constant threat of smaller predators. Then, gradually darkness, pressure, cold, and the arrival of the one threat that will follow it all the way down. The juvenile colossal squid filmed in 2025 looked nothing like a monster. Researchers described it as resembling a glass sculpture. Delicate, fragile, almost ethereal, floating through the darkness. Its body was nearly completely transparent. Light passed through rather than reflecting off. The squid was close to invisible. This transparency is not accidental. It is an adaptation shared by the entire glass squid family, to which the colossal squid belongs. In an environment where predators hunt by sight, being see-through provides tremendous advantages. A transparent animal casts no shadow. It creates no silhouette against faint light from above. It essentially vanishes. The mechanism is remarkable. The tissues contain almost no opaque materials. Pigment cells called chromatophores are present but minimized. Internal organs are arranged and colored to reduce visibility. Even the blood contains compounds that absorb rather than reflect light. Everything conspires to let photons pass through unimpeded. Scientists observing the 2025 footage noted something particularly exciting. The juvenile squid displayed chromatophores, those color-changing cells that allow other cephalopods to alter their appearance rapidly. This means the colossal squid almost certainly can switch between transparency and opacity depending on circumstances. Imagine the tactical flexibility this provides. When hiding from visual predators, the squid can be invisible. When ambushing prey that might see through its body, it can become opaque. When communicating with others of its species, it can flash patterns or display solid colors. The chromatophores give it options that pure transparency would not. This ability has never been observed directly in an adult colossal squid. The specimens examined were dead and preserved. Their chromatophores were no longer functional. But the presence of these cells in juveniles strongly suggests adults retain them. The capability exists even if we have not seen it used. The transition from transparent juvenile to opaque adult involves the development of thicker muscle tissue. Adult colossal squid need stronger bodies to handle large prey and survive encounters with predators. This muscle mass inevitably reduces transparency. Adults are probably not invisible the way juveniles are, but they may retain enough chromatophore function to modulate their appearance in useful ways. In the pitch black of the bathypelagic zone where adults live, transparency becomes less valuable anyway. No sunlight penetrates those depths. There are no silhouettes to hide. The visual hunting that transparency defeats does not occur in total darkness. Adults need different adaptations than juveniles, and the loss of transparency coincides with the acquisition of those adaptations. But during the vulnerable juvenile phase, being invisible matters enormously. Young colossal squid face threats from fish, seabirds, marine mammals, and potentially adults of their own species. Their hooks and suckers are not yet fully developed. Their bodies are small enough to be swallowed whole by many predators. Transparency is their primary defense during the years when they have few others. The glass-like body also hints at something beautiful about deep-sea evolution. Under crushing pressure and freezing temperature, life has produced creatures that look like art. The colossal squid juvenile floating through darkness is as elegant as any sculpture in any museum. Form follows function even when function creates breathtaking form. The transformation is dramatic. A colossal squid begins life as a transparent wisp that could fit in your palm and potentially ends as an 1,100-pound predator that leaves scars on whales. Understanding how this growth happens reveals the squid's entire life strategy. Juvenile colossal squid are essentially floating in the richest parts of the water column. They eat constantly by squid standards, taking in the calories needed to build tissue rapidly. Their transparent bodies minimize predation risk while they accumulate mass. Every successful meal is converted to growth. During this phase, the squid's body remains soft and delicate. The hooks on the tentacles and arms are present but not yet at full size. The beak is functional but small. The eyes, proportionally large even at this stage, continue developing the extreme sensitivity they will need later. The organism is building the machinery of predation while depending on camouflage for survival. As the squid grows, it begins descending. The transition happens gradually over months or years. 500 feet, 1,000 feet, 1,500. With each downward movement, the environment changes. Light fades, pressure increases, temperature drops toward freezing. Prey becomes scarcer. Predators become fewer, but more dangerous. The body adapts. Transparency gives way to opacity as muscles thicken. The ammonia concentration rises to maintain buoyancy at greater depths. Metabolism slows to match reduced food availability. The frantic feeding of youth transforms into the patient waiting of adulthood. Size increases follow a pattern we can only partially reconstruct from the specimens available. Scientists estimate that the largest confirmed individual, the 1,100-pound female captured in 2007, was not yet fully mature. Larger beaks found in whale stomachs suggest adults may exceed 1,500 pounds. Getting from birth to maximum size probably requires several years, though the exact timeline is unknown. The growth curve is not linear. Young squid in food-rich shallow waters probably grow faster than adults in the sparse deep. There may be seasonal variations tied to prey availability. There may be individual differences based on luck, location, and genetics. The squid we have examined represents snapshots, not lifelong observations. What we know with certainty is that the transformation works. The species has existed for millions of years. Individuals successfully navigate from vulnerable, transparent juvenile to armored adult predator, often enough to maintain the population. The strategy of vertical migration and gradual development produces functional outcomes. But this growth has limits we can only guess at. How large can a colossal squid actually get? The beaks suggest animals somewhat larger than any we have captured, but how much larger? Are there individuals exceeding a ton somewhere in the darkness? Is the 1,100-pound specimen close to maximum size or barely halfway there? The deep keeps these answers hidden. We have studied this species for a century and still cannot say how big it grows, how long it lives, or how many exist. The transformation from glass baby to shadow giant happens in waters we cannot easily visit, recorded by no cameras we have deployed. Each colossal squid that completes this journey becomes something that should not exist by the rules of the world we know. A creature built entirely from ocean nutrients, assembled in freezing darkness, armed with biological weapons that spin and grip and cut. It sounds like fantasy, but these animals are real, growing right now in the deep Antarctic, approaching sizes we have never directly measured. And eventually, each one encounters something even larger. Something that has been eating colossal squid since before humans existed. Picture a fish the length of a grown man, over 6 feet from head to tail. More than 200 pounds of cold muscle, armed with needle-sharp teeth. The Antarctic toothfish is one of the most formidable predators in the Southern Ocean. And it shares a relationship with the colossal squid that scientists are only beginning to understand. They eat each other. This is confirmed. Researchers examining both species have found remains of toothfish inside colossal squid stomachs and remains of colossal squid inside toothfish stomachs. The predator-prey relationship runs in both directions, depending on which animal is larger at the moment of encounter. Between 2011 and 2014, commercial fishing vessels brought up 8,000 Antarctic toothfish from southern ocean waters. Scientists examined each one carefully. 71 of those fish bore unmistakable evidence of colossal squid attack. Circular scars matching the serrated suckers, parallel scratches matching the spacing of those rotating hooks. These fish had fought a colossal squid and survived to tell the story in scar tissue. The math here reveals something important. 71 out of 8,000 means less than 1% of toothfish showed attack evidence. This suggests colossal squid do not encounter or attack toothfish frequently. When attacks happen, they often fail. The fish escapes. The squid goes hungry. The ambush predator strategy does not guarantee success. But when attacks succeed, the meal is substantial. A single toothfish provides enough calories to sustain a colossal squid for weeks, given that slow metabolism. One successful hunt can make up for many failed attempts. The energy math favors patience over persistence. The relationship flips based on life stage. A juvenile colossal squid is small enough for an adult toothfish to swallow. An adult colossal squid is large enough to kill and consume a juvenile toothfish. Size determines who plays predator and who plays prey. The roles reverse as both species grow. This creates evolutionary pressure in both directions. Toothfish that avoid squid attacks survive to reproduce. Colossal squid that successfully hunt toothfish gain the calories needed to reach maturity. Each species shapes the other through millions of years of deadly interaction. The scars on surviving toothfish are evidence of an arms race still underway. Geographic distribution binds these species together. Both thrive in the same cold, deep waters around Antarctica. The Ross Sea supports substantial populations of each. The Cooperation Sea region shows particularly high colossal squid activity. Where one species succeeds, the other typically does too. Their fates are linked by the environment they share. Commercial fishing operations accidentally revealed this connection. Colossal squid are attracted to hooked toothfish, struggling on long lines. The squid sees an easy meal and attacks. Sometimes the squid becomes entangled itself. Several colossal squid specimens came to science this way, captured while trying to steal from human fishing operations. This opportunism tells us something about the squid's hunting behavior. It does not distinguish between naturally struggling prey and prey caught by humans. The ambush instinct triggers regardless of context. A toothfish in distress looks like food, whether distress came from the squid's own attack or from a steel hook. Scientists have also found evidence that both species compete for the same prey. Smaller fish and squid make up significant portions of both diets. When colossal squid and toothfish share territory, they are not only eating each other, but also eating each other's food supply. Competition and predation overlap in ways that complicate simple food web diagrams. The toothfish connection provides one of our best windows into colossal squid behavior, because we cannot easily observe the squid directly. But we can examine toothfish that survive attacks. We can count scars and measure wounds and calculate strike patterns. The fish become recording devices for encounters that happen in total darkness beyond any camera's reach. But neither toothfish nor colossal squid sits at the true top of this food chain. Something else hunts both without worrying about size or life stage. The discovery was disturbing but not entirely surprising. When scientists examined the stomach contents of a colossal squid captured in the Prides Bay region of Antarctica, they found tissue that could only have come from one species, another colossal squid. The animal had been eating its own kind. Cannibalism appears throughout the cephalopod world. Octopuses consume each other regularly. Many squid species treat smaller members of their own populations as acceptable food sources. The behavior makes harsh sense in environments where meals are rare and calories precious. When you encounter something edible, you eat it. Genetic kinship provides no exemption, but colossal squid cannibalism raises particular questions because of how rarely these animals seem to meet. Adults are scattered across millions of square miles. Population density appears low based on capture rates. Finding another colossal squid should be difficult. Finding one small enough to safely attack should be even more difficult. Yet the stomach evidence proves it happens. The most likely scenario involves adults preying on juveniles or subadults. The size difference between life stages is substantial. A mature female weighing 1,000 pounds dwarfs a juvenile weighing 50. The hooks and beak that work on toothfish would work equally well on smaller squid. From the adult's perspective, a juvenile of its own species represents calories like any other prey. This creates an evolutionary tension that threatens population stability. Adults that eat their own offspring reduce their genetic legacy. Species that consume too many juveniles risk collapsing their own numbers. Some mechanism must limit cannibalism, or the colossal squid would have destroyed itself long ago. The vertical migration pattern may provide that limitation. Juveniles occupy shallower water than adults. The depth separation keeps generations apart through most of the year. Adults rarely ascend to where juveniles live. Juveniles have not yet descended to adult depths. The populations effectively exist in different worlds. Cannibalism probably occurs during transition periods. A juvenile moving into deeper water might encounter an adult before completing its descent. An adult ascending for unknown reasons might find itself among smaller individuals. These overlap moments create opportunities for one generation to prey upon another. The hooks make more sense in this context. Catching a struggling squid, even a smaller one, requires extraordinary grip strength. Hooks that rotate maintain contact despite violent resistance. 3 pointed barbs on the arms prevent prey from sliding free. These weapons evolved to hold things that fight desperately for survival. Other colossal squid would fight exactly that way. Scientists cannot determine how frequently this cannibalism occurs. One documented case proves it happens, but reveals nothing about regularity. The species might be routinely cannibalistic, with adults commonly preying on juveniles they encounter. Or cannibalism might be rare, occurring only when other food is completely unavailable. The sparse population density suggests occasional rather than constant self-predation. If colossal squid regularly consumed each other, population numbers would face severe pressure. Reproduction would need to dramatically outpace self-predation. The species' continued existence implies cannibalism remains a minor component of overall mortality. But even occasional cannibalism changes how we understand this animal. It is not merely a victim of sperm whales and a predator of fish. It is a predator of itself. The weapons that kill toothfish can kill smaller members of his own species. The eyes that watch for approaching whales also watch for approaching adults that might see a juvenile as food. Those enormous eyes serve defense in every direction, against threats from other species, against threats from their own. 17. That is the confirmed number of predator species that include colossal squid in their diet. Scientists have documented its remains in the stomachs or waist of penguins, various albatrosses, multiple seabirds, several fish species, and an assortment of marine mammals. Something is always trying to eat this animal at every stage of its life. But here is the detail that changes the picture completely. Almost all that predation targets juveniles. Only 2 predator types regularly take adult colossal squid: sperm whales and southern sleeper sharks. Everything else on the list of 17 is eating young, small individuals that have not yet descended into the protective deep, where adults spend their lives. This pattern makes sense when you consider what hunting an adult requires. A fully grown colossal squid lives below 3,000 feet in water that would crush most predators. It weighs hundreds of pounds and defends itself with hooks capable of leaving permanent scars on whale skin. It has eyes that detect approaching threats from 400 feet away. Successfully killing such an animal demands capabilities few species possess. Sperm whales have those capabilities. They dive deeper than any other mammal on Earth. They use echolocation that the squid cannot hear. They have bodies massive enough to absorb hook damage without slowing down. They have been hunting deep-sea squid for millions of years and have perfected every technique the task requires. Southern sleeper sharks are less understood, but appear similarly specialized. These slow-moving giants reach lengths exceeding 20 feet. They inhabit the extreme depths where adult colossal squid live. They may use stealth and patience similar to the squid's own ambush strategy. The darkness that conceals the squid also conceals the approaching shark. Everyone else is limited to eating juveniles. Penguins dive impressively, but cannot reach adult depths. Albatrosses find dying squid floating near the waterline, likely individuals in their final hours. Toothfish and other large predatory fish take juveniles small enough to swallow whole. None of these predators can follow the squid into its mature refuge thousands of feet below. This creates a survival bottleneck at the juvenile stage. Young colossal squid face pressure from 17 different directions. Fish below, birds above, mammals throughout. Every successful juvenile must navigate this gauntlet while growing large enough and descending deep enough to escape. Those that reach adult size and depth enter a safer world. Only 2 predator types can threaten them there. The odds of survival improve dramatically, but the 2 remaining threats are formidable beyond anything the juvenile stage has faced. Sperm whales are among the most effective hunters the ocean has ever produced. They find colossal squid with sonar the squid cannot detect. They attack with jaws large enough to swallow an adult squid in pieces. Sleeper sharks are poorly understood, but clearly dangerous. They patrol the same depths and feed on similar prey. The 17 predator list also reveals the colossal squid's ecological importance. This single species supports a significant portion of the Antarctic food web. Birds depend on it. Fish depend on it. Mammals from penguins to pilot whales depend on it. Removing colossal squid from the ecosystem would send ripples through food chains across multiple trophic levels. Scientists use predator diet analysis to estimate squid abundance. If 17 species routinely find and eat these squid, the population must be reasonably healthy, despite our difficulty observing it directly. A genuinely rare species could not sustain so many predators, but abundance means nothing to the individual squid facing a sperm whale. The population survives. Many individuals do not. 50 tons of hunting mammal descending through absolute darkness. Echolocation clicks louder than jet engines mapping everything below. The largest brain of any animal that has ever existed, calculating approach angles and attack timing. This is the sperm whale, and it has been eating colossal squid since before humans learned to walk upright. The relationship is ancient and reciprocal. Sperm whales evolved specifically to hunt deep-sea squid. Their enormous heads contain acoustic equipment tuned precisely for locating soft-bodied prey, where no light reaches. Their teeth grip rather than chew, because they swallow squid whole or in large pieces. Their diving capabilities exceed any other air-breathing animal, because the prey they need lives at crushing depths. Colossal squid made sperm whales into what they are. The evolutionary pressure of hunting something that large, that deep, that well-defended shaped everything about whale anatomy. Every remarkable feature of sperm whale biology traces back to the demands of finding and eating squid. The reverse is equally true. Colossal squid eyes grew to soccer ball dimensions because sperm whales hunt them. The 400-foot detection range evolved because whales approach from beyond that distance. The ink defense, the freezing behavior, the descent into deeper and deeper water with age, all of it represents evolutionary response to whale predation pressure. These species shaped each other through millions of years of violent interaction. The arms race continues today in encounters no human has witnessed directly. When they meet, the battle is brief. The whale tracks the squid with sonar from distances exceeding half a mile. The squid remains deaf to this approach. Only when the whale gets close enough to disturb bioluminescent organisms does the squid detect danger. By then, the whale has already committed to attack. What happens next leaves evidence we can examine. Sperm whales surface bearing circular scars and parallel scratches across their skin. These marks match exactly the size and spacing of colossal squid suckers and hooks. The squid fought back. It wrapped its arms around the whale's head. It dug in with every weapon evolution provided. The battle raged in total darkness at depths that would instantly kill a human. The whale wins almost every time. Size advantage makes the outcome essentially predetermined. An 1,100-pound squid against a 50-ton whale faces odds comparable to a house cat attacking a grizzly bear. The hooks leave marks. The suckers grip and cut. But the whale consumes the squid regardless. Scientists suspect whales may use focused sound bursts to stun squid before the final strike. The acoustic equipment that enables echolocation could potentially produce blasts intense enough to disorient or briefly paralyze soft-bodied prey. A stunned squid would be easier to catch than one fighting at full capacity. The numbers tell the predation story clearly. Colossal squid beaks represent 14% of all squid beaks found in Antarctic sperm whale stomachs. Given the colossal squid's massive body size, this means roughly 77% of the total squid biomass these whales consume comes from one species. Sperm whales in Antarctic waters survive primarily by eating colossal squid. The whales need the squid to exist. The squid cannot prevent the whales from killing them. The relationship continues. Generation after generation, neither species capable of destroying the other completely. Somewhere in Antarctic darkness right now, this battle is happening again. The evidence is written across their bodies. Sperm whales swimming through Antarctic waters frequently display distinctive markings on their skin. Circular depressions matching squid sucker diameter. Parallel scratches, matching hook placement and spacing. These permanent records tell stories of encounters that occurred in total darkness, thousands of feet below. Scientists have studied these markings for decades. The circular scars are straightforward to interpret. Colossal squid suckers create suction to grip, and the serrated edges cut into tissue as they hold. When the whale survives, wounds heal into permanent evidence of their size and position. You can measure a scar and estimate the sucker that made it. The hook scratches provide additional information. Colossal squid arms bear hooks arranged in specific patterns. The scratches on whale skin match these patterns precisely. Researchers can sometimes estimate the attacking squid's size based on spacing between marks. Larger squid have wider hook separation. The geometry tells part of the story. Most scars concentrate on the head and forward body. This makes sense given attack dynamics. The whale approaches head first, using jaws to seize prey. The squid wraps arms around whatever it can reach, which is primarily the attacking head. Hooks dig in, suckers grip. The battle leaves concentrated evidence in the strike zone where contact is greatest. Some whales show extensive scarring accumulated across decades. A sperm whale can live 60 years or more. An individual that spends its life hunting colossal squid bears evidence of countless encounters. The density of marks indicates both hunting success and the ferocity of squid resistance. Every scar represents a fight the whale survived. The scars grow as the whale grows. A mark made in youth stretches as skin expands over decades. This stretching confused early researchers. They measured old, distorted scars and calculated squid dimensions that seemed impossibly large. Sucker marks that appeared a foot across led to estimates of squid hundreds of feet long. Later work recognized the distortion and corrected calculations downward. The marks prove something important about colossal squid behavior. These animals do not surrender passively. Facing a predator 50 times their mass, they attack. They wrap arms around whatever they can reach. They dig hooks into flesh. They inflict damage that persists for the predator's entire remaining life. The hooks cannot kill a sperm whale. They are defensive weapons, not offensive ones. But they cause pain. They draw blood. They leave permanent reminders. If even marginal deterrent value exists, natural selection would favor squid that fight hardest and leave deepest marks. Scars also appear on whales that beach themselves and can be examined in detail. Dead sperm whales washing up on coastlines sometimes display attack evidence clearly. Scientists can photograph marks precisely, measure dimensions exactly, and collect tissue samples from scar margins. These strandings provide research opportunities impossible with living whales. The marks vary between individuals in ways that might indicate different hunting patterns or different populations of squid. A whale that feeds in one region might show different scarring than one that hunts elsewhere. Geographic variation in scar characteristics could reveal squid population structure we cannot measure directly. Every mark is a data point. Every data point is a battle. Every battle happened in conditions humans cannot survive, at depths we barely reach, between animals we can scarcely imagine. The scars are permanent records of an ongoing war. They confirm that somewhere in Antarctic darkness, these encounters continue right now. The whales bear witness, the squid leave their marks, and the story writes itself in flesh. Let that number sink in. In Antarctic waters, sperm whales derive the majority of their calories from colossal squid, not from fish, not from the dozens of other squid species available. One animal provides most of what keeps 50-ton mammals alive in some of the harshest waters on Earth. Scientists calculated this figure by analyzing stomach contents from sperm whales taken during commercial whaling before international protections ended the practice. They counted beaks, which survive digestion and accumulate over time. They measured each beak to estimate body mass of the consumed squid. They converted mass to calories and compared across species. Colossal squid beaks represent only 14% of total beak count. Numerically, other squid species appear more frequently, but the colossal squid's enormous body means each individual delivers far more calories than smaller species. When measured by biomass rather than by beak number, colossal squid dominate the diet. 77% of all squid mass consumed. This dependency creates ecological vulnerability for both species. Sperm whales in the Southern Ocean essentially require colossal squid to survive. No other prey provides comparable caloric returns for the energy invested in deep diving. If colossal squid populations crashed, whale populations would face severe stress. The relationship works in reverse as well. Sperm whales are the primary predator of adult colossal squid. They probably kill more individuals annually than all other predators combined. If whale populations increase dramatically, squid numbers would likely decline. If whales disappeared, squid might multiply unchecked until other limiting factors emerged. This predator-prey linkage ties both species to forces beyond their control. Commercial whaling reduced sperm whale populations substantially during the 20th century. That reduction probably allowed colossal squid numbers to increase, though baseline data does not exist to confirm this. Now that most whaling has ended, whale populations are slowly recovering. Predation pressure on squid is presumably rising in response. The 77% figure also reveals hunting efficiency. Sperm whales are extremely good at finding and catching colossal squid, despite all the squid's defenses. Those enormous eyes, the depth refugees, the attempted escapes, none of it prevents whales from successfully hunting these animals at industrial scale. Consider what successful hunting requires. The whale must find a squid scattered across millions of cubic miles of ocean. It must track the squid using sonar the squid cannot hear. It must approach close enough to strike despite the squid's visual early warning system. It must capture and consume an animal armed with hooks that leave lasting damage. And it must repeat this process successfully enough that colossal squid constitute most of its diet. Sperm whales accomplish this through abilities we struggle to measure. acoustic processing that builds three-dimensional maps from echo returns, diving physiology that permits extended operation at crushing depths, hunting strategies refined across millions of years of evolutionary pressure from squid that continuously improve their defenses. The colossal squid cannot match these abilities. It detects threats, it flees when possible, it fights when cornered. But ultimately, it is food. The numbers do not lie. 77% of biomass consumed means the largest toothed predator on Earth depends on the largest invertebrate for most of its survival energy. Neither species can exist without the other. The whale needs the squid as prey. The squid population depends on whale predation, keeping numbers in check with food availability. They are locked together by energy flow through Antarctic ecosystems. What affects one inevitably affects the other. The eternal war continues because both sides need it to continue. Deep within every sperm whale's digestive system lies a graveyard. Squid beaks made of tough chitin resist breakdown and accumulate over the whale's lifetime. Each beak represents one consumed individual. Scientists count these remains to reconstruct what whales eat and how much. The colossal squid beak is the largest of any known squid species. It operates like a parrot's beak, with upper and lower portions that shear past each other to slice tissue. The structure is robust enough to cut through fish flesh and squid muscle, and it is durable enough to survive years inside a whale's stomach, while everything else digests away. When researchers examine whale stomach contents, colossal squid beaks stand out immediately. Nothing else approaches their size. Identification is simple. 55 colossal squid beaks have been formally documented from whale stomachs and related sources. Some are considerably larger than the beak from the biggest complete specimen ever captured. This beak evidence reveals something unsettling. There are colossal squid in Antarctic waters larger than any we have directly examined. The calculations suggest individuals potentially exceeding 1,300 pounds, possibly approaching 1,500. These giants exist only as beaks in whale digestive tracts. We have never seen their bodies. Beak growth rings function somewhat like tree rings, potentially allowing age estimates. Scientists have attempted similar analysis on colossal squid beaks with limited success. Results suggest these animals may live longer than typical squid, perhaps multiple years rather than the standard 1 to 2 year lifespan. But sample sizes remain too small for confident conclusions. The beaks provide dietary information about the squid as well. Chemical analysis of beak material reveals what the squid ate before it became prey itself. Isotope ratios indicate trophic level, confirming colossal squid status as apex predators. Trace elements suggest geographic range and feeding patterns during the animal's life. Every beak is a data point. Every data point constructs understanding of an animal we cannot study directly. The beaks inform estimates of size distribution, age structure, dietary habits, and population dynamics. They are fossils of individuals consumed within living memory, preserved by digestive chemistry that destroyed everything else. Accumulation patterns matter as well. Beaks collect faster when whales hunt more frequently. A whale with many colossal squid beaks has succeeded in many hunts. Changes in beak accumulation rates across whale populations might indicate changes in squid availability. Fewer beaks could mean declining squid numbers or shifting distributions. Some beaks show damage from final moments. Chips and cracks may result from capture impacts or crushing force from whale jaws. These marks record violence too brief for observation, but permanent in structural evidence. The beak that survived digestion also survived the attack that killed its owner. The relationship between beaks and complete specimens creates an unusual research situation. We know more about dead colossal squid than living ones. Beaks tell us about size, age, diet, and abundance. The few complete specimens tell us about anatomy and physiology. Together they provide fragments of understanding. Separately they highlight how much remains unknown. Somewhere in Antarctic darkness right now, a colossal squid is being consumed. Its body will dissolve. Its beak will persist. Eventually that beak may reach scientists who will add it to the count. Knowledge built from remains of the eaten. Understanding constructed from survival of the indigestible. The beaks tell the story of those who lost the eternal battle with whales. March 9th, 2025. The date that changed everything researchers thought they understood about observing the unobservable. On that day, cameras aboard an underwater robot recorded clear footage of a colossal squid swimming freely in its natural habitat. 100 years after scientists first described this species, humans finally witnessed it alive where it actually lives. The location was remote. The South Sandwich Islands in the South Atlantic Ocean, a chain of volcanic peaks surrounded by some of the least explored waters on Earth. A research vessel called Falkor, operated by the Schmidt Ocean Institute, had deployed a remotely operated vehicle named Seibel to survey marine life. The team was not hunting specifically for colossal squid. They were exploring an understudied region for any discoveries it might offer. Seibel descended to nearly 2,000 feet. Its cameras recorded the darkness, capturing whatever drifted through the lights. Then something appeared that made researchers gasp audibly. A squid. Translucent. Delicate. Unmistakably a species no camera had ever recorded alive at depth. A viewer watching the live stream from thousands of miles away recognized what they were seeing and immediately contacted experts. Within hours, independent scientists had confirmed the species' identification. The distinctive hooks visible on the arms matched nothing else. This was a colossal squid, the first ever filmed in its natural environment. The individual was small, about 12 inches long, a juvenile that had not yet descended to the depths where adults spend their lives. Its body appeared almost completely transparent, allowing internal organs to be seen through the skin. Scientists watching the footage used words like beautiful and delicate and glass sculpture. Monster was notably absent from descriptions. Why did confirmation take a full century? The explanations stack upon each other. The Southern Ocean is vast beyond comprehension. The squid lives at depths requiring specialized equipment. Its sensitive eyes probably detect and avoid the lights research vehicles require. It may freeze motionless when threatened, becoming nearly invisible against dark water. Every adaptation helping survival also helps evasion. Previous possible sightings existed but lacked verification. Footage from 2023 showed something that might have been a colossal squid, but image quality was insufficient for confirmation. Fishermen had filmed dying specimens hauled up accidentally. Scientists had studied fresh, dead individuals in meticulous detail. But living behavior in natural conditions remained unrecorded until this moment. The footage duration was brief, only minutes before the squid drifted beyond camera range. No pursuit was attempted. The research team simply watched, recorded, and recognized the historic significance of what their screens displayed. The coincidence of timing seemed almost intentional. 2025 marked exactly 100 years since Robson formally described the species from arm fragments found in a whale's stomach. A century of wondering what this animal looked like while alive finally ended on an anniversary that felt designed by fate. The footage proved direct observation is achievable. The technology works when conditions align. The approach works when luck cooperates. Future expeditions can attempt to replicate success with lessons learned from this encounter. 100 years of mystery. Minutes of footage. Everything changed. The word colossal carries psychological weight. It suggests something massive, powerful, terrifying. When people imagine the colossal squid, they picture Kraken mythology. Tentacles dragging ships beneath the waves. Sailors screaming as hooks dig into flesh. The monster of nightmares made real in Antarctic darkness. The footage from 2025 showed something entirely different. The juvenile colossal squid on camera appeared fragile, delicate, almost ethereal as it drifted through the water column. Its fins were so thin they barely registered on video. Its movements were slow and graceful rather than violent and aggressive. One researcher described the experience of watching as like observing a glass ornament suspended in black water. This gentleness contradicted a century of assumptions built from preserved specimens. Scientists had studied the fierce hooks on dead animals. They had examined massive beaks capable of slicing fish. They had documented scars these creatures leave on whale skin. Everything suggested an aggressive predator, a creature of violence perfectly designed for combat in the deep. The living squid suggested something else, an animal that conserves energy by moving minimally, a hunter that waits rather than chases, a species that fights when cornered but drifts unseen through darkness as its default existence. Researchers have revised their understanding accordingly. The colossal squid probably spends most of its life doing very little, floating, watching with those enormous eyes, waiting for opportunity or threat to change circumstance. The hooks and beak are tools for rare moments when violence becomes necessary. They do not define routine existence. The transparency reinforced this revision. An animal evolved to be invisible is not seeking confrontation. The glass-like body developed to avoid detection by predators and to ambush prey. Aggression would undermine both strategies. Drawing attention through dramatic movement contradicts the fundamental design of the organism. The enormous eyes make new sense in this context. They are warning systems rather than hunting tools. They evolved primarily to detect approaching threats, not to spot distant prey. A true monster would not need such elaborate escape mechanisms. A prey animal surviving against superior predators would. The colossal squid occupies both roles simultaneously. It hunts effectively when opportunity presents. It is hunted effectively by larger predators. Its body reflects this duality perfectly. Hooks serve hunting needs. Giant eyes serve escape needs. Transparency serves both by making encounters less likely in either direction. The monster mythology will persist regardless of evidence. Stories of Kraken sell more than stories of patient drifting. Media coverage of the footage still used words like creature and beast and fearsome, despite what the video actually showed. Human psychology prefers drama over accuracy when ancient fears surface, but scientists now understand differently. The colossal squid is remarkable for what it actually is: an organism supremely adapted to impossible conditions, a survivor in one of the harshest environments on Earth, a living demonstration that evolution finds solutions human engineers cannot imagine. Not a monster, not a kraken, something stranger, something more interesting, something real. The juvenile colossal squid in the 2025 footage revealed something scientists had theorized but never confirmed in a living specimen: chromatophores. Those specialized cells allowing cephalopods to change color, pattern, and texture with remarkable speed and precision. This discovery matters enormously because chromatophores require living tissue to demonstrate function. Once an animal dies, the cells collapse and become useless for study. Examining preserved colossal squid told researchers nothing about whether color change capabilities existed or how they might operate. The footage changed that understanding completely. Scientists observed chromatophores clearly distributed across the juvenile's mantle. The cells appeared as small, rusty, red-brown spots scattered along the body. Their presence confirms colossal squid possess the same rapid color change technology, making other cephalopods famous for visual communication and camouflage mastery. The implications reshape assumptions about behavior. A colossal squid with functional chromatophores can almost certainly switch between transparency and opacity depending on circumstance. The juvenile appeared mostly transparent during observation, but those chromatophores could expand to block light and create solid coloration instantly when needed. Why would a deep-sea animal need color change ability in waters where no light penetrates? Several explanations make biological sense. Juveniles live in shallower water where some light exists. Transparency provides excellent camouflage against visual predators hunting from below, but camouflage against bioluminescent detection might require different approaches. Chromatophores could allow rapid strategy switching depending on perceived threat type. Adults may use chromatophore displays for communication despite the darkness. Mating encounters between individuals that rarely meet would benefit from clear visual signals. Flash patterns indicating species identity, sex, and reproductive readiness could help colossal squid recognize potential mates in sparse populations. Chromatophore patterns might startle predators or prey during critical moments. A sudden transition from invisible to visible could provide crucial seconds during escape attempts. Surprise alone might create survival advantages worth the biological cost of maintaining specialized cells. The patterns themselves may carry meaning we cannot interpret. Other cephalopods use chromatophore displays for complex signaling scientists are still decoding. Colossal squid might have similarly sophisticated communication systems operating in darkness where observation is impossible. The footage showed chromatophores essentially at rest. The squid was not actively changing color during the recorded period. Scientists suspect it either remained unaware of the camera or assessed the vehicle as non-threatening. Either way, the full capability of the system remains unknown. Adults might display different patterns than juveniles. As bodies transition from transparent to opaque during maturation, chromatophores probably become more prominent and essential for signaling. Color change ability supplementing transparency in youth might become critical for communication in adulthood. Testing these ideas requires more observations. The single footage event confirmed chromatophore existence but showed almost nothing about use. Future encounters might capture color changes in action, finally revealing what these cells actually accomplish. Until then, imagination fills the gaps. What? Patterns flash in deep Antarctic waters? What signals pass between giants humans have rarely glimpsed? What conversations occur in colors we have never witnessed? The chromatophores exist. Their purpose remains hidden in the same darkness concealing everything else. The colossal squid brain surprises anyone expecting simple nervous tissue. The brain itself is not exceptionally large relative to body mass. Cephalopods generally have smaller brains than vertebrates of comparable size. But the organization of the colossal squid brain tells a story about evolutionary priorities, revealing how this animal experiences its world. The optical lobes dominate everything. These structures process visual information from the enormous eyes, and in the colossal squid, they are massive. Scientists examining preserved specimens documented optical lobes larger than the entire visual cortex of a human brain. More neural real estate devoted to seeing than to any other sensory function. This disproportionate investment makes biological sense, given survival requirements. Vision is how the colossal squid survives. Those soccer ball eyes gather photons in environments where photons barely exist. The optical lobes convert gathered information into actionable awareness. Is that faint shimmer a prey animal's bioluminescence? Is that disturbance pattern a descending sperm whale? The brain must answer instantly and correctly every time. Wrong answers mean death. The optical lobe architecture suggests sophisticated processing capabilities. These are not simple relay stations forwarding raw data. They contain multiple layers of neurons arranged in patterns enabling complex analysis, edge detection, motion tracking, distance calculation. The biological equivalent of computer vision software, refined across millions of years for one specific purpose: survival in darkness. The rest of the brain appears less remarkable by comparison. Motor control regions coordinate 8 arms and 2 tentacles, but nothing indicates unusual complexity. Learning and memory areas exist, but remain unstudied in meaningful detail. The colossal squid apparently invested neural resources heavily in vision, potentially at the expense of other cognitive capabilities. This specialization aligns with ambush predator lifestyle. An animal that waits rather than actively planning does not necessarily need sophisticated higher reasoning. It needs detection. It needs threat assessment. It needs accurate striking when opportunities present. The visual-heavy brain provides exactly these capabilities efficiently. The optical lobes also integrate information from the photophores mounted beside each eye. The squid must coordinate light production with light detection, distinguishing its own illumination from external sources. This integration probably happens within the optical lobes themselves, creating unified visual awareness, including the squid's contribution to ambient conditions. Scientists have speculated about colossal squid intelligence with minimal evidence. Cephalopods generally demonstrate remarkable problem-solving capabilities. Octopuses escape enclosures, use tools, and recognize individual humans. But these behaviors appear in species that can survive in captivity. No researcher has kept a colossal squid alive long enough for cognitive testing. The large optical lobes suggest visual intelligence specifically, pattern recognition, object tracking, spatial reasoning. These represent genuine cognitive functions, even if they differ from the tool use intelligence capturing human attention. The colossal squid may lack cleverness in forms we recognize while possessing sophisticated capabilities in forms we undervalue. The brain architecture also raises philosophical questions. What does existence feel like for an animal whose neural structure centers on visual processing? Does the colossal squid experience its world as streams of imagery? Does awareness exist beyond stimulus and response? These questions lack answers with current knowledge, but they become more compelling when you recognize how much of this creature's nervous system evolved to serve a single sense. The pressure would kill you instantly. At 7,000 feet below sea level, every square inch of surface bears over 3,000 pounds of force. Your lungs would collapse. Your bones would crack. Nothing evolved for land survives these depths without protection humans cannot provide. The colossal squid thrives here. Scientists have confirmed adult colossal squid presence at depths exceeding 7,200 feet, based on beaks recovered from sperm whale stomachs. The whales that dive this deep return bearing evidence of squid encounters. The hunting grounds extend into realms that remain nearly unexplored by human technology. What are conditions like at these depths? Temperature hovers barely above freezing regardless of season. Absolute darkness prevails because sunlight cannot penetrate this far under any circumstance. Pressure alters every chemical reaction in biological systems, slowing processes and changing protein behavior. The water feels dense enough to seem thick, though no human has experienced it directly. Life persists despite these conditions. Bioluminescent organisms provide the only illumination, generating sporadic glow the colossal squid's eyes evolved specifically to detect. Fish adapted to extreme pressure swim slowly through the void. Crustaceans scavenge organic material sinking from productive waters far above. The ecosystem is sparse but functional, sustained by constant rain of dead matter from the sunlit world. The colossal squid fits this environment perfectly. Its ammonia-rich tissues provide buoyancy independent of swim bladders, which would compress dangerously under extreme pressure. Its slow metabolism matches reduced energy availability in the deep. Its cold-blooded physiology tolerates temperatures that would incapacitate warm-blooded hunters. The depth gradient provides defense. At 7,000 feet, few predators can follow. Southern sleeper sharks reach these depths, as do sperm whales during their deepest dives. But most organisms that might eat colossal squid simply cannot descend this far. The crushing pressure excludes them. The deep itself functions as armor. Scientists believe adult colossal squid spend most of their existence in the bathypelagic zone, between roughly 3,000 and 10,000 feet, occasionally descending deeper when circumstances require. The rare specimens captured in shallower water were probably migrating, mating, or following unusual prey distribution. Normal adult life happens far below human observation capability. This depth preference explains why the 2025 footage showed only a juvenile. At roughly 2,000 feet, The camera operated near the upper boundary of Colossal Squid range. Adults would have been thousands of feet further, down, invisible to equipment unable to reach them. Filming a full-grown individual in its true habitat requires technology barely existing. What else lives alongside the colossal squid at these depths? The Southern Ocean's bathypelagic zone remains poorly documented. Sperm whales hunt there. Sleeper sharks patrol. Various fish species occupy ecological roles we have barely identified. The complete community structure, the full network of who consumes whom at 7,000 feet, remains largely mysterious. The colossal squid shares its world with organisms we have not yet named. In the darkness where it waits, other eyes may watch that we have never observed. The deep keeps its secrets behind pressure walls we cannot easily breach. Antarctica produces giants. The colossal squid is the heaviest invertebrate on Earth. Antarctic krill swarms contain more biomass than any other animal aggregation measured. The waters surrounding the frozen continent support whales, seals, and seabirds in concentrations that dwarf populations elsewhere. Something about extreme cold encourages organisms to grow enormous. Scientists call this phenomenon polar gigantism. They have debated its causes for decades without reaching complete consensus. The leading explanation involves oxygen availability. Cold water holds more dissolved oxygen than warm water. Oxygen is essential for cellular metabolism. Greater availability allows cells to grow larger without suffocating from insufficient supply. Bigger cells build bigger bodies. This explanation works particularly well for cold-blooded animals like the colossal squid. Warm-blooded organisms bring internal oxygen delivery systems and face different constraints. But invertebrates and fish, depending directly on environmental oxygen, benefit from cold water's enhanced carrying capacity. Temperature also influences growth duration. Cold environments, slow metabolisms, extending lifespans and delaying reproductive maturity. An animal taking longer to reach breeding age has more time accumulating body mass. The colossal squid's extremely slow metabolism, requiring only an ounce of food daily, permits extended growth periods impossible in warmer regions. Food availability contributes as well. Antarctic waters support tremendous productivity during summer months when continuous sunlight drives explosive phytoplankton blooms. This productivity cascades through food chains, supporting dense prey populations. Predators with access to abundant food can grow larger than those in food-limited environments. The colossal squid benefits from all these factors simultaneously. Cold water provides oxygen. Slow metabolism extends growth windows. Abundant prey during juvenile stages in shallower water allows rapid mass accumulation. The Antarctic serves as ideal factory conditions for manufacturing the world's largest invertebrate. Other polar giants support this general explanation. Arctic and Antarctic waters contain the largest jellyfish species, the largest sea spiders, the largest amphipods. The pattern repeats across taxonomic groups. Whatever drives polar gigantism affects diverse lineages similarly, but not everything grows large in polar waters. Some species remain small despite identical conditions. Size involves trade-offs varying between organisms. Energy requirements increase with body mass. Larger animals need more food even with slow metabolisms. In environments where prey availability fluctuates, being excessively large might become disadvantageous during lean periods. The colossal squid apparently found optimal balance, large enough to dominate its ecological role and resist most predators, small enough that minimal food requirements can be met through occasional successful hunts. The 1,100-pound specimens captured may represent ideal size rather than maximum achievable size. Scientists suspect the largest individuals are females. Sexual dimorphism, where one sex grows larger, appears commonly in squid species. The biggest confirmed colossal squid was female. The beaks suggesting even larger animals have not been sexed, but they might derive entirely from exceptional females, rather than indicating general population of giants. The polar gigantism explanation raises climate change concerns. As Antarctic waters warm, oxygen carrying capacity decreases. Will this affect colossal squid growth potential? Could future generations be smaller than ancestors? The species survived ice ages and warming periods historically, but current change rates may pose challenges unlike anything in its evolutionary experience. The cold made the giant. What happens when the cold retreats? No scientist has witnessed colossal squid mating. No researcher has discovered eggs confirmed as belonging to this species. No one has documented courtship rituals, spawning sites, or parental behavior. The reproductive biology of the colossal squid remains almost completely unknown a full century after its scientific description. This knowledge gap is extraordinary given what we understand about other squid species. Many squids have been observed mating in natural conditions or laboratory settings. Their eggs have been collected and raised. Their reproductive timing is well documented. But the colossal squid lives too deep, too scattered, too difficult to find for standard reproductive research. What little we know comes from examining internal organs in captured specimens. Females possess ovaries containing thousands of eggs. Analysis suggests eggs are fertilized internally and probably released as a floating mass similar to related species. The eggs likely drift in the water column until hatching produces tiny larvae beginning life, far from where adults exist. Estimated egg size is approximately 3 millimeters in diameter. This seems small for such an enormous animal, suggesting high fecundity balanced against high offspring mortality. A female may release thousands of eggs, accepting that most will never reach maturity. Reproductive timing remains uncertain. Some evidence points toward Antarctic summer spawning when conditions favor larval survival. Ovulation appears synchronous, meaning females release all eggs in a single event rather than multiple batches across extended periods. This pattern is common in squid species with brief lifespans and one-time breeding. Male anatomy provided unexpected findings. Most male squid possess a hectocotylus, a specialized arm modified for storing and transferring sperm packages to females during mating. The few male colossal squid examined lacked this structure entirely. Instead, they appeared to use a penis for direct sperm delivery. This anatomical difference suggests different mating behavior than most squid species. Hectocotylus-equipped males can transfer sperm from some distance. Penis-equipped males require close physical contact. The colossal squid's mating posture and encounter duration remain completely unknown. Scientists attempt inference from related species. Other glass squid family members provide some guidance, but the colossal squid's extreme size and depth preference may require unique reproductive adaptations absent in smaller relatives. Finding mates presents obvious challenges. Adults live scattered across millions of square miles. Population density appears low. How does one colossal squid locate another ready and willing to mate? Bioluminescence probably helps. The eye-mounted photophores could generate species-specific signals, attracting potential partners across significant distances. Chemical cues released into water might indicate reproductive readiness. Many marine organisms detect pheromones, signaling willingness to mate. The chromatophores might serve reproductive communication in adults. Color change displays could convey sex, condition, and intent in ways that standardize encounters between individuals meeting rarely. Until observation occurs, these remain speculation. The reproductive secrets of the world's largest invertebrate hide in the same darkness concealing everything else about its existence. The absence became obvious once scientists examined specimens carefully. Male colossal squid lack a hectocotylus. This specialized arm modified for sperm transfer appears in virtually every other squid species. Its absence suggests something fundamentally different about colossal squid reproduction. In typical squid mating, males use their hectocotylus to package spermatophores and deliver them to females. The arm tip may be highly modified with grooves, flaps, and sucker alterations specific to transfer function. Some species can pass sperm from considerable distance. Others require direct contact but benefit from the arm's specialized design. The colossal squid apparently reproduces differently. Male specimens possess a penis instead of a modified arm. This organ requires much closer contact during mating. The male cannot deliver sperm from arm's reach. Physical connection with the female becomes necessary in ways other squid species avoid. Why this difference evolved remains unclear. One possibility involves the colossal squid's unique weaponry. Those hooks and serrated suckers covering the arms could make hectocotylus transfer dangerous. A male reaching toward a female with arm modifications might trigger defensive responses. Direct penis transfer could prove safer for both participants. Another possibility relates to environmental conditions. Deep, cold, high-pressure water might affect spermatophore viability in ways favoring direct delivery. Sperm packets exposed during hectocotylus transfer might have lower fertilization success than sperm deposited directly into the female's body. Close contact required for penis mating suggests something about colossal squid encounters. When males and females meet, they apparently approach closely despite both carrying weapons capable of causing serious injury. Some mechanism must prevent mating attempts from becoming battles. Courtship behavior probably serves this function. Most cephalopods use elaborate rituals, signaling intent and readiness before physical contact. Color changes, posture modifications, and specific movement patterns communicate mating interest rather than aggression. The colossal squid likely has similar protocols despite no human observation. Size difference between sexes may also contribute. Female colossal squid appear larger than males based on limited specimens. This dimorphism is common across squid species. A smaller male approaching a larger female faces reduced risk compared to equally sized individuals confronting each other. The penis transfer method raises questions about mating duration. Hectocotylus-equipped species can complete sperm delivery in seconds. Penis mating might require extended contact. How two large squid armed with hooks maintain proximity long enough for successful fertilization remains mysterious. Scientists have found spermatophores implanted in female tissue. These sperm packages indicate successful mating occurred before capture. Placement suggests males target specific body areas for implantation. Females store sperm until environmental conditions favor egg fertilization. Every piece of reproductive information derives from dead specimens. Living reproductive behavior remains entirely unwitnessed. Males without hectocotylus exist in scientific descriptions, but have never been observed using their alternative equipment. Until cameras reach depths where mating occurs, colossal squid reproductive secrets remain as concealed as everything else about this species' life. The males are different. Why remains unanswered. Count them yourself. The total takes seconds. By 2015, only 12 complete colossal squid had ever been recorded in scientific literature. 12 individuals recovered from millions of square miles of ocean across 90 years of knowing. The species existed. This scarcity defines everything about research limitations. Scientists cannot conduct population studies with 12 specimens. They cannot analyze age distributions or growth patterns. They cannot compare individuals across regions or seasons with meaningful confidence. Sample size is simply too small for statistical power. Why are complete specimens so rare? Multiple factors combine making collection extraordinarily difficult. The colossal squid lives at depths most fishing equipment never reaches. Commercial trawlers working Antarctic waters typically operate shallower than adult squid territory. Accidental captures occur only when squid venture unusually high or when gear descends unusually deep. These coincidences are rare. The squid attacks hooked fish on long lines. When it strikes at struggling toothfish, it sometimes becomes entangled itself. But long line caught squid are frequently damaged during capture. They may have fought lines for hours before surfacing. Stress and physical trauma often destroy scientific value before researchers can examine anything. Getting specimens to scientists intact requires preparation. Fishing vessels often lack. A colossal squid hauled aboard begins decomposing immediately in warmer air temperatures. Without proper freezing equipment and trained personnel, the animal deteriorates before meaningful examination becomes possible. The Southern Ocean is remote beyond easy access. Research vessels operate there infrequently. Commercial ships that could capture squid may lack resources or motivation for specimen preservation. Colossal squid have zero commercial value. The ammonia-rich flesh is unpalatable. Economic incentive to preserve captured animals evaporates quickly. The specimens we have resulted from fortunate coincidences. Fishing boats with freezer capacity happening to catch squid near operational areas. Research cruisers encountering specimens unexpectedly, dying animals floating close enough, to inhabited regions that someone noticed and responded appropriately. The largest specimen, the 1,100-pound female captured in 2007, was frozen whole aboard a New Zealand fishing vessel. The crew recognized significance and took extraordinary preservation measures. That single decision enabled the most detailed colossal squid examination ever conducted. 55 beaks have been collected from various sources, predominantly whale stomachs. Beaks survive digestion and environmental exposure better than flesh. A beak on the seafloor may eventually reach somewhere discoverable, but beaks tell only partial stories. Anatomy, physiology, and recent diet require complete bodies. The specimen shortage constrains understanding fundamentally. We cannot determine natural variation because we have seen too few individuals to measure it. We cannot describe population structure confidently. We cannot track changes over time. We study this animal through glimpses, so infrequent that each one generates headlines. The 2025 footage represented a new kind of specimen, a video rather than physical collection. Behavioral information rather than anatomical data. As underwater technology advances, visual observation may become the primary research method. Waiting for fishing boats to capture individuals accidentally may give way to systematic camera surveys. But physical specimens will always matter for certain questions. Genetics requires tissue, reproduction requires organs, diet requires stomach contents. The 12 complete specimens and 55 beaks remain the foundation supporting everything we claim to know. A century of investigation, and the questions vastly outnumber answers. How long does a colossal squid actually live? We cannot say with confidence. How many individuals exist across the Southern Ocean? We lack data for reliable estimates. What does a healthy adult look like swimming freely at 7,000 feet? No human has ever witnessed it. The colossal squid remains one of the most mysterious large animals on our planet. The catalogue of unknowns humbles anyone claiming expertise. We have never observed mating. We have never confirmed eggs. We have never tracked an individual across time. We have never measured maximum swimming speed. We have never recorded responses to encountering another colossal squid. We have never witnessed a whale battle from the squid's perspective. These gaps matter beyond academic curiosity. The colossal squid functions as a keystone species in Antarctic ecosystems. It feeds whales, seals, fish, and seabirds across multiple life stages. It consumes fish that humans harvest commercially. It occupies ecological niches affecting nutrient cycling and energy transfer throughout the Southern Ocean. Understanding this animal means understanding the system containing it. Climate change intensifies urgency. Antarctic waters are warming faster than most ocean regions globally. Oxygen. Concentrations may decrease as temperatures rise. Prey distributions may shift unpredictably. The conditions producing colossal squid across millions of years are transforming over mere decades. Will the species adapt successfully? Will populations decline? Will distributions migrate? Without baseline knowledge, we cannot even formulate the right questions. The deep ocean generally remains Earth's least explored environment. We possess better maps of lunar surface than seafloor topography. Humans have spent more time in space than in bathypelagic zones. The colossal squid exemplifies this ignorance. An animal weighing half a ton hides successfully in waters we have barely visited. The 2025 footage cracked open a door, demonstrating that direct observation is achievable, changes research approaches fundamentally. Autonomous underwater vehicles could survey colossal squid habitat systematically, rather than depending on accidental encounters. Baited camera systems might attract individuals into view reliably. Machine learning could analyze thousands of footage hours, searching for the distinctive glass squid silhouette. These methods require substantial investment. Deep sea research costs enormously. Equipment capable of operating at 7,000 feet requires millions in funding. Expeditions to remote Antarctic waters demand months of planning and massive logistical coordination. Scientific communities must decide colossal squid research merits the necessary resources. The species also serves as ambassador. When people learn about colossal squid, they learn about deep oceans more broadly. The eyes the size of soccer balls, the hooks rotating on swivels, the battles with whales in absolute darkness. These details capture imagination in ways abstract oceanography cannot achieve. A creature this remarkable justifies the claim that wonders remain undiscovered. Every unknown represents opportunity. Every knowledge gap marks space where the next researcher could generate discoveries rewriting textbooks. The colossal squid has guarded secrets for 100 years. It will not surrender them easily. But the pursuit teaches things worth knowing. About the deep ocean. About evolution under extreme conditions. About the boundaries of life itself. About our own planet and how little of it we truly comprehend. The colossal squid drifts somewhere right now in Antarctic darkness, watching with eyes evolved to detect approaching death, waiting with hooks ready to grip whatever approaches, living a life no human has witnessed across the entire century since we learned its name. What it knows about the deep, we may never fully share, but every glimpse brings us closer. Every specimen teaches something new. Every frame of footage illuminates darkness that has hidden too much for too long. The mystery continues, and that is precisely why it matters.